9.2, we're going to be taking a look at multi-stage experiments. Now, we didn't exactly describe 9.1 as single-stage or one-stage experiments, but we did do just one-stage experiments. So I'll define what that is in just a moment, but the first thing I want to describe is how we're going to be processing through, for the most part, with our multi-stage experiments. So what we're going to be using are tree diagrams. And they're not like factor trees, if you're thinking of those kinds of trees where you like break numbers down. It's not like that. But a tree diagram is a sample space model where each of the outcomes is designated by a separate branch. And it's descriptive, and it's also numerical. Okay, so we're going to have both pieces of information on our tree branches. One-stage experiments is actually what happened in 9.1. So one-stage experiment is like if you draw a name out of the hat and you draw one name. You roll the die and you roll them one time. Okay, so you're doing something just once. Experiment over after one step. In terms of the pictures, we don't really need tree diagrams, but if you did them, they'd have one set of branches. Two-stage experiments are experiments that are over after two steps. Okay, so you draw two names out of the basket. You roll the dice twice, or you flip the coin twice. You have two children instead of one child, right? So anything that happens in more than one step is multi-stage. Two steps is the one this one's describing, so there's two. All right, multiplication rule for tree diagrams. So for all multi-stage experiments, the probability of an outcome along any path of a tree diagram is equal to the product of all probabilities along the path. All right, so what's the probability that you're going to roll a 2 and then you're going to roll a 3? Well, you multiply each of those outcomes together, and that's how you get the outcome of both of those things happening. There's a note here, and it's kind of a fuzzy note. It says, I expect to see tree diagrams or something equivalent, that's why it's fuzzy, in order to show the work on what you're doing. So you can use a tree diagram all the time. It's an option. But there are some problems that I'm going to show you where there's sort of an alternate thing to do, an alternate perspective that does the equivalent sort of thing that would be acceptable, okay? But there should be some kind of diagramming work, and most of the time it's tree diagrams, for every single problem you do. Even if you know how to do it conceptually without the tree diagram, and here's why. If you're working with those early middle school students, which is where they would see this for the first time, probability usually shows up in about 7th grade. I know some of you are sitting here saying, I'm not teaching 7th grade math, Dr. Hans. That's okay. You're still certified all the way up to 8th grade math. Did you know that? Yeah, so have to make sure that if you end up in that environment, you can do something about it, right? It's good stuff. That's how they do it. They do it with tree diagrams. They don't have the higher level thinking that you do to be able to support it without that. Does that make sense? And that's why we're going to be doing it that way. Okay. Independent events are events which occurrence of one event has no influence on the outcome of the second event. We can think of lots of examples of independent events. We'll write a few of them down, both game-like and real-life-like. So an example of an independent events would be rolling dice. Or likewise, you could say flipping coins. If I flip the coin once, it has no bearing on what the coin does the second time I flip it. If I roll the die once, there is no reason that roll of the die has any effect on the next roll. Okay? We know that to be true. That's why those kinds of, especially the die, is used in games, is because it's supposed to be randomized, right? We want it to be completely random. But there's lots of real-world situation stuffs, too, that would work here. So we'll say it just as birth of kids. My son and his wife, they're having a girl. That has absolutely no bearing on if they have child number 2, whether it's going to be a girl or a boy, right? It doesn't. There's absolutely no effect of the one child's gender on the next child's gender, none. And so an example of things maybe, some sort of non-examples, if you want to jot these down, I won't write them down, but you can write them down. Some non-examples. Generally, the weather today has some bearing on the weather tomorrow, unless you're in Oklahoma, right? Usually does. It's 70 degrees outside today, which is way better for a soccer game than the 20 degrees they were supposed to do on Thursday last week, I'm going to say. Right? Weather generally affects from one day to the next. And it does affect in Oklahoma too. I'm just being a little bit silly. But, right, like there's an effect. What happened today has some effect on what happens tomorrow. If you are drawing names out of a hat, so imagine we put everybody's names in here out of a hat. We're essentially going to do this when we do our choosing our presentations. I lost the word. Thank you. The presentations that we're going to have. We're going to put your names in. You're going to draw them out one at a time. If everybody's names go in, and as soon as we draw out Aubrey's name, we don't put it back in, which we wouldn't because that wouldn't make sense. She's not doing two presentations, right? No, right? That would actually be something that's not independent, right? The second drawing out of a name is affected by the first drawing out of a name. But can you imagine in a classroom where all you're trying to do is you're randomly selecting people's names and you don't really want to pull Aubrey's name out and then she just like shuts down and disengages because she knows she's not going to get called again, right? You don't really want that. So you put her name back in so that she still could be pulled out again. Y'all with me? That'd be independent. Because now the effect of drawing her name out the first time has absolutely no effect on the ability that she has to be drawn out a second time. Okay? So the context matters, right? But also the way in which that we're, in this case, like drawing the names out of the hat doesn't really fall into either category all the time. It depends on the other constraints you place on it. All right. If you have independent events, then the probability that the two events occur sort of like back to back or in succession is the multiplication of those probabilities. So right now we have 18 people in class today. So if I put all of your names in and I drew out one name, you have a 1 out of 18 chance of being drawn. That's the way it would work. Okay, you learned that in 9.1. But if I put, like if I did Aubrey's and I put Aubrey's name back in a second time, there's still a 1 out of 18 chance that everybody has of being drawn again, right? Like that still happens. So we would multiply 1 out of 18 times 1 out of 18. And if you multiplied those together, that would be your chance of being drawn twice. It's not real high, but that's how you would calculate it. Okay, everybody good so far? Okay. I think, yeah, okay, good. All right, we have an example. So this example is the idea of kind of drawing names out of a hat, so to speak. We have an executive committee of 10 members. There are 4 women and 6 men. 3 members are selected at random to attend a meeting in Hawaii. You want to go? Yeah, that'd be great. We should do that, right? We should all take a trip to Hawaii. Okay, so when we reach in, and maybe I should make mention of the fact here, that if you take a look at the questions that are being asked afterwards, it helps you to know how to draw your tree diagram. These questions are all based on whether it was a man or a woman's name that was drawn. So while there are 10 separate individuals' names who can be drawn, the questions don't specifically ask about them individually. They only ask about them in regard to one characteristic. Okay? So the questions say, what is the probability all selected are women? What is the probability at least one man is selected? Yeah, those are our 2 questions. Okay? So when I draw my tree diagram, I lose some of the individuality of the characteristics of, in this case, the people. All that I'm being asked to answer questions about is whether it's a man or a woman. So when I draw my tree diagrams, my branches for my tree diagrams, I only need to draw branches that represent their gender. So the first set of branches, I reach into the basket and I pull out a name, and it's either the name of a man or a woman. So you can use M and W, male and female, man and woman. I don't care what you want to use. I'm going to put male for M and then F for female. So M and F, that's what I'm going to do. Okay? All right, so if I reach in and I draw out a man, how many men are in the basket? 6. How many people are in the basket total? 10. So there is a 6 out of 10 chance that the first name I draw out is a man's name. Are you with me? Okay. What's the likelihood of drawing out a female's name, a woman's name? 4/10. This is a set of tree diagram branches. Okay? Notice if I add them together, what am I going to get? 10 out of 10, which is equal to 1. Every set of branches has to add up to 1. Okay? That's the way that these are created. Every set has to add up to 1. Now, once I draw a person's name out of the basket, am I going to put it back in? No. They're already on their trip to Hawaii, or at least they're already in the grouping of people who get to go. I don't need to put their name back in. Okay? So I am going to draw another person's name out, but that original person's name is not going to be in there. So how many people are going to still be in my basket of names when I make my second draw? 9. So the second draw will be made. It will be made no matter what happens on the first draw. Sometimes I don't have like equal branches on the top and the first, on the second draw or something like that for something. We'll see an example of that. But again, my options are to either draw a male or a female. But these set of branches are different because these set of branches actually have to take into consideration what happened on the first set of branches already. So if I go along the top branch, I already drew one man's name out of the basket. How many men are still left in there? There's still 5. And how many names are in there total now? 9. How many women's names are in there? Still 4. The same 4 we originally had out of still 9, because there's still only 9 names. So now I have 5 ninths and 4 ninths, and does it still add up to 1? It does. But what happens down here is not the same, right? If I come down this set of branches, the woman's name was drawn the first time. So how many men are still left in the basket on the bottom set of branches? There's still 6. And how many names are total in there? 9. How many women's names are in the basket now? 3. Out of how many? 9. Still adds up to 1 though, right? But the numbers themselves don't match. Some tree diagrams are going to have the same number on every branch. We'll see an example of that. This one doesn't do that because every event depends on what was done before. Right? These are dependent events, and this is how we can parse them out so that we can actually put numbers associated with them. All right, this only gets me 2 people going to Hawaii, and I'm supposed to have how many? Okay, not 4. I think it's 3, isn't it? Okay, 3. I just want to move this over a little bit. Okay, 3 people going to Hawaii. So we're going to do one more set of branches to draw our third name out. These tree diagrams, if you make the branches longer, you buy yourself more space. If you're making them really short branches, it's really hard to fit it all in there. You do not have to move from left to right. You can move from top to down. Like sometimes I have people who like to draw their tree diagrams. Let me switch so you can see. Who like to draw their tree diagrams like this. Okay, you can do that too if you prefer. Either way is fine, but keep in mind as you're working that if you skip something, skip some space. Because when you go back and fill it in with whatever information you didn't know how to do originally, you're going to need a block of space to do the tree diagram, okay? All right, all of the ends of my tree diagrams are still going to say male and female, just like they did on the first ones. Okay, but again, depending on which direction I go and what happened will depend on the numbers. So if we go along the entire top, I've drawn out 2 men, right? I drew a man for the first time, I drew a man for the second time. So how many men's names are still left in the bucket at that point? 4. How many names are in the bucket? 8. So there's 4 out of 8. How many women's names are still in there? The same 4 that were the whole time, right? Poor ladies. 4 out of 8 still in there. Okay, how about the second set of branches? So along this set of branches, and I'm going to highlight, I've drawn out 1 male and 1 female. Does everybody see that okay? All right, so then how many men's names are still in the basket? 5. We started with 6. We drew out 1, so we're left with 5. So we have 5 out of 8. How many women's names are still in there? 3 out of 8. Now, while we did it in a different order, this branch right here is exactly the same thing. I drew a woman's name and then a man's name, but the end result is I have 2 different ones that I've drawn, right? So it's actually going to match the previous set of numbers that I had because I've drawn 1 of each at that point. So how many men are still left in there? 5. And women? 3. Okay, last branch down here. I've drawn along that branch 2 women's names, 2 female names. So how many male, I don't know, how many guys are still in the bucket? 6, yes. And how many girls are still in that bucket? There are only 2 at that point. Okay, does this make sense? Is that right? It requires you to do some thinking along the way. You can't just slap numbers down. It doesn't work. Please make a note to yourself that every set of branches adds up to 1. It happens all the time where people forget that detail and they do something different. But we're in a position now where we can actually answer the questions that were asked on the next slide. It says, what is the probability that all three selected are women? So do you see the branch that represents that outcome? Where is it? It's at the very bottom. This branch right here is selecting 3 women to go to Hawaii. All good? Okay, well, we had a theorem right here, 9.6, that says, for all multistage experiments, the probability of an outcome along a path, that's the blue I just highlighted, is equal to the product of the probabilities along that path. So that's telling me that in order to find the outcome I'm now looking for, I'm going to multiply those 3 probabilities together. 4 over 10, 3 over 9, and 2 over 8. Okay? So I need to multiply 4 over 10, 3 over 9, and 2 over 8. Now, you're welcome to multiply across the top, multiply across the bottom. If you want to do that, that's okay. I'm going to reduce as I go, so I don't have to have such large numbers that I'm working with. Do you see any numbers either within the fraction itself or across diagonals that can be reduced? What do you see, Kiki? The 4/10. What can I divide them both by? 2. So if I divide them both by 2, I now have 2/5. Okay, somebody else tell me another fraction that you see that we can simplify. The 3/9. Yes, Miranda, what will I divide the 3 and the 9 by?
Sorry.
It's okay.
I said 2/8. So
You said 2/8. Well, then let me do the 2/8 with you. What will you divide the 2/8 by?
it'll be 1/4.
It'll be 1/4. Yeah, we'll divide them each by 1. Who said the 3/9 then? Aubrey, what did you want to do with the 3/9? Fabulous. Divide them both by 3 to have 1/3. At this point, if you wanted to multiply across the top, that would be okay. There is one more simplification we could do. Does anyone see what it is? It's not within a single fraction this time. You could do the 2 and the 4 here. Right? Across the diagonals, you could divide them both by 2. That would be fine. We won't, since I'm seeing some people looking at me like, why is she doing that? So we're just going to do it this way. So let's just multiply across the top. 2 times 1 times 1 is 2. On the bottom, 5 times 3 is 15. Do you know 15 times 4? It's 60. Good. All right, 2 60ths, and then we would be able to divide them both by 2, right? So I would get 1/30. That's not very likely, right? That's not a very likely thing. If you wanted to turn it into a decimal just to kind of give yourself some perspective, right? That's like 3% chance, give or take. Not real likely that there's 3 women going to Hawaii, okay? Now, the second question said, what is the probability of at least one man being selected? Now, this does not say there's exactly one man going. It says at least one. What does that mean? So it could be all men. It could be one man, which would be down here would be one man. Here would be one man. Here's one man as well. Those are all one men. And then there's this option right here that's got 2 men on it. Oh, and this one too. This one has 2 men in it. Oh, this one's got 2 men in it. You got it. It's literally everything that I didn't already find. It's everything except for this one down here that we already found. Everything. So, in any scenario, if we're looking at possible outcomes, what you learned in 9.1 is that everything ranges between 0 and 1, right? It's like 0% and 100%. This is the decimal or the fractional perspective of it. That's what a probability is, okay? So it's between 0 and 1. So all of these branches, if I were to multiply along every single branch, I know what the outcome is along the bottom one because we already did it. It's 1 out of 30. But if I multiplied every single branch out and I added them all together, what should I get? 1. This is all the outcomes. 1 means 100%. So if I multiplied every single branch together and added them all up, I will get 100% or the number 1. So instead of actually finding 7 different multiplications and adding them together, because all that sounds like it's going to take a long time, Any idea how I could answer the question that the second one here, part B, is asking? Yes. Instead of doing this, I can take this as 1 minus the probability of all women, which is what I found in the previous step, 1 out of 30. Much faster answer if I do subtraction. And you had a probability theorem back in section 1 that told you this. Okay? What is 1 minus 1 out of 30? It is 29 out of 30. It's 29 out of 30. You can either do that from the perspective of fractions, change them to have common denominator, or ask yourself, what am I missing from the 1 to equal the number 30? We have 29 out of 30. Okay, I think that this is actually a really good place to stop because our next one delves into something that doesn't look like a tree diagram. So we will pause here.